Sunju Kim from Yonsei University will talk about shepherding slots to object toward stable and robust object-centric learning. Please give him a big round of applause.
Thank you for the introduction. Once again, my name is Sunju Kim from Yonsei University. The title here is a little too grand in a sense. That's the title of our research project, where there are about 10 research teams all over Korea that are participating in this project. So the research goal, the ultimate goal of our research project is to develop System 2 AI through neurosymbolic inference. So we want to basically combine deep neural networks with symbolic AI. And as an application of our hybrid AI, we want to apply this to video analysis for online streaming video understanding, and especially understanding the causal relationship between the events and user queries, and also providing logical explanations. So this is basically saying why we need to go to System 2 AI. The biggest problem with the current deep learning technology is that they're not really good at modeling the causal relationship. So we kind of want to go to that causal relationship with a little bit of symbolic AI. Okay. So how do we want to go to symbolic 2 AI? First, we want to propose a method that prioritizes task-specific modeling, enabling the deep neural networks to train in the absence of ground truth data. Second, we want to work on object-centric learning to secure foundational technology for symbolic inference. And then we want to work on videos. So now I want to specifically talk about number 2, the object-centric learning. So this is a work that we published at this CVPR this year. And the title is called the Shepherding the Slots to Objects Towards Stable and Robust Object-Centric Learning. So first, let me introduce you the task of OCL. Okay, so this is, I guess, in a way, relatively a new task in machine learning and computer vision. So given an image, here we go. So given an image, the output of an OCL algorithm should give you a segmentation, right? So there are about 3 objects in the input image. So the output would be segmentation of the objects, and each object should have a representation in a vector. Okay, so it's a very similar to image segmentation task, but the big difference from the original paper here is that this is unsupervised text. So you're not given any segmentation mask to do this. Given an image, you want to come up with a very nice representation of each object without any ground truth. Okay, so there are single view image object-centric learning, and there's also multi-view object-centric learning, and also they do this for videos. In a way, solving this object-centric learning for videos or even for multi-view images, they're a little bit easier because they have more information, right? So you can get some more cues or inductive bias from other frames or other views. But with the single view image, you don't really have an inductive bias here. You just somehow need to come up with a soft segmentation of objects and their representation. So the main methodology that we all use for OCL is called the slot attention. So it basically employs the concept of slots, which is just a set of vectors. And basically what it does, it's just an attention algorithm. Okay, so given an image, it's first encoded, and then the encoded vectors go through an attention mechanism with the slot vectors. I guess the key difference here with the slot attention to the regular attention that people use is when you kind of employ attention, it's usually kind of employed for the spatial dimension, right? So you basically add all the attention value for all the pixels, and it should sum up to 1, right? But for slot attention, attention actually goes depth-wise, right? So all the attention depth-wise should be equal to 1. So basically, what goes on is, so you have your slot vectors, right? And then basically all the slots are competing per pixel. So per pixel, basically slots are saying, oh, this pixel belongs to me. Oh, wait a minute. And then other slots will say, hey, that's mine, right? So after a few iterations of this slot attention, basically all these slots will be basically attending to a very specific objects. Okay, so that's slot attention. So the problem with this slot attention is that it's quite unstable during training because it really doesn't have any assumptions or bias or any information to use to do this, right? So basically what may happen is that like every training, you may end up with different results and your segmentation result may not be so accurate. So we call that as bleeding or attention linkage problem, where some of the pixels in an object may be identified as a background or vice versa. Right? So as you can see, some of the slots may actually capture the background. And overall, if you look at the attention map, they may not be so stable. So our goal when we actually started to work with the OCL was to first, let's just do a better job of segmenting these objects, right? So because if we use previous works on OCL, they actually give you the result like this. But we wanted to have the object segmentation to work much stable, okay? So we propose an algorithm called SLASH, and so the big, I guess, keyword here is shepherding. So basically, we basically use two ideas. First is to give object-related inductive bias by using a practical supervision. So I said like the original OCL is just purely unsupervised work, and that's just too hard. So basically, we are going to weekly semi-supervision, giving few data ground truths, not for all the data that we are using, but about 60% of the data, we provide some information about the ground truths, but we don't give like the full segmentation map. We only give point per object when we actually want to give some more inductive bias, okay? And another thing is, as I have just showed you on the previous slide, there will be a lot of bleeding or linkage in the segmentation. So basically what we want to do is when the slots are doing its attention, we are kind of doing shepherding, right? We don't want pixels to deviate and go to other pixels. So we call this as slot attention via shepherding. So our idea is very simple. We are basically adding two models to the original slot attention algorithm. So one is called the ARC, and the other one is called the IPPE. And I'll basically be talking about these two models. So first is the attention refining kernel. So as I said, all slot attention is doing is just, as you can see, the key query value attention, but the attention is just on another dimension, right? And the problem that we face is that when it's doing its attention, it's not a very nice map because the points are spread around and here and there. So as a result, what we want is we don't want this segmentation result. We want them to be nicely grouped, right? So funny story here is if you just look at the input and output, this is a very basic binary image processing, right? I don't really know how many of you have actually learned traditional machine vision textbook. But like back in the days, probably 30 years ago, one of the first things that we learn is how to process binary images. And we learn concepts like opening and closing, dilation and stuff. Right, and this is just a pure kind of like the prime example of binary image processing. So I told my student that was working on this project, say, well, there's this concept of dilation from very long time ago, and I gave him this textbook called Machine Vision. And he worked on it, and he actually got pretty good result. And he was like, wow, there is something like this that actually works without actually doing any of neural network stuff, right? But we didn't actually use that. Of course, we need something learnable. So we employed a learnable low-pass filter that, given this kind of spread around binary map, we can actually give you a very nice grouped set of points in this binary image. So those are basically your segmentation result for each of the slots per object. And one thing about the slot attention here is, if you look at the original framework here, there's an iteration going on here. So actual slot attention runs several times with the recurrent neural networks. So it's actually updating the slot several times. So after each iteration, what we do is we ensure that their position is actually on the objects. So we are kind of giving more information as weak semi-supervised way, because previously they were just doing this unsupervised way. So we are just giving them just point information about where the objects are. And this 2D position is only provided for 10% of the entire data set, and also for 75% of the objects that are present in these images. So the idea is actually very simple. All we do is we are giving more information about where the objects are through point information, and also this low-pass filtering that is learnable. And let's see the results. So these are the original result. As you can see, the segmentation map are not very sharp. And as you can see, using this slash method, we get much better segmentation results. And another, so here are some of the quantitative results. As we can see, we beat all the numbers. But what's really significant about the result is, one of the problems of the previous method is that their standard deviation is too high. So every time you train this, you get different results. And they would only run like 3 experiments for most of the previous works. But for all these data sets, we actually ran this for 10 times. And we ended up with the lowest standard deviation, meaning that our method is more stable. And as the numbers indicate, our algorithm seems to be the most robust for object-centric learning. So let's say through this slash algorithm, we got stable segmentation. So what do we do next with the object-centric learning? So this is something that we are working on right now. And so there is OCL, and we can also kind of call this as the binding problem. So the binding problem is a fundamental problem, well, not in computer science, but in computer vision, originated from the cognitive science. And it's a way to represent the real world in a computationally friendly manner. So given an image like this, you kind of have to do segregation or segmentation, come up with nice representation per object. But in the end, you have to understand the composition of the scene with all this representation. So this is kind of like old David Marr's vision, right? Compositional computer vision. So I don't really know if this is really the right way to go, or especially where like this large language models and vision language models are working so well. But I think it's still kind of something that we should still look at, right? So we want to do this composition understanding of the scene with the object representation. So here are 3 cores of the binding problem. One's segregation, or basically how to segment the image into different objects. Second problem is how do you represent those objects? And then you have to understand the composition and also how to use those objects representation. So we kind of solve the segregation problem in the previous paper. And number 2 and number 3 is something that we are currently working on. And we are working on towards building something that is interpretable and also controllable with the object representation learned from the slot attention. So basically what we want to do is, so through the slot attention, we kind of found where the objects are and we have their representation, right? So to make this more useful, we want to basically play around with those vectors so that we can change the position and the size and the colors or some different properties of those objects, okay? And well, you could probably do this if you have a large data set with image captioning, which is probably related to the previous talk, right? But we don't have that data here, okay? So how do we do this? So one way you can do this, there are a very few previous work on this, but if you can kind of reverse engineer the vectors here, you may do a little bit, right? So this is kind of like inverse scan, right? So you reverse engineer and change different elements of these vectors and see what actually changes. But that's actually very limited. So what we are doing, so basically we don't have the ground truth for training all this stuff, all this manipulation. So what we want to do is we want to basically use a self-supervision and also image augmentation to be able to control this representation. So basic idea is, so here's your slot and the representation of each objects. And so after you reconstruct the original image from this representation, you can compare with the original image, measure the loss here. And this is basically where you can train your slot attention here. But now to be able to play around with this representation, what we do is we basically have another model. This is basically an adapter, right? So this is an adapter, just a very simple neural net model that changes your representation, that can do something with these slots so that they actually change a little bit. And so basically the representation here becomes an input, this update model, but there's also instruction coming into this slot update. And instruction, for example, could be like move your number 1 objects to the left by 10 pixels, change the color of the object number 2 from red to blue or something. So this is kind of like having the representation and the instruction in language as an input. And this will give you something. And how do we actually measure the loss is we know what the instructions are, right? So we basically kind of apply this instruction to original image, basically change our original image based on the instruction. And this output of this slot update should actually be equal to the output from the instruction. Right? So this is totally a self-supervised method to manipulate the object's representation. So here are the results. So given an initial image like this on the left, and if you give instructions like this, as you can see, you can change the location. You can also make it bigger. And there's this Tetris data set. So we can actually play around with Tetris and play actually the game of Tetris with the given language instruction. Okay. So, and there are further questions. How do we actually work without any object level supervision? So to solve the slash, we actually had to give some type of supervision. Can we do this without any supervision is one question that we still have. And another question is, how can you extend this observation into more complex and usable application? And the biggest bottleneck with the image level object-centric learning right now is it only actually works on synthetic data, right? If we try to do this with real images, it just doesn't work, right? So it somewhat works with the multiple view images or maybe in videos, but for images, we haven't seen any work that can actually do this on any real data. So how can we apply this into real images is a big question mark. And one direction really may be, to use the vision language model. It seems like the VLMs are really very expressive, very powerful. So it's probably useful to kind of adopt VLM for this object-centric learning as well, right? And of course, as I said in the beginning, our main application field will be to videos. And so how do we incorporate this representation learning, manipulation, causalities into the videos is also a big question mark, okay? All right, that's it for me today. And if there are any questions, I'll be glad to answer them. Thank you very much.
Thank you, Sanju, for your great talk. So now we are going to have a Q&A session. Please raise your hand if you have any questions. Okay, so I have some simple questions. So because this session is about foundational AI, so maybe you know that these days we have some foundation models for segmentation, for example, SAM, right? So my question is that the motivation for OCL is still valid? I mean, even existing of such powerful foundation model?
I think the thing is like our goal is not really to do segmentation. It's really about how can you learn the right representation for a computer vision problem. And I know that like something like SAM and all these large models, the foundation models are pretty good at doing their own tasks, but I don't really know if they're actually solving the representation problem. They are coming out with some representation that's really good for solving a very specific task, but I don't know if they're actually coming out with the general representation of objects, or maybe for videos, their actions and so on, something that we can tackle around with, and especially for kind of finding out the causal relationship between objects and different people.
Any other questions? Okay, thank you, Sanju, again for your great talk. Yeah. So as the last talk of this session, Professor Chung-Sun Hong from Kyunghee University will talk about faster segment anything, actually, which was I asked before, toward the lightweight SAM for mobile application. So please give him a big round of applause.
Thank you, Chaeyoung, for your kind introduction for me. Okay, the title of this talk is Faster, the segment anything toward lightweight SAM for mobile applications. Yes. Okay, my talk is include the some of proposal and then some real applications of the our proposal. Okay, this slide shows the history of the vision segmentation models. Since the introduction of the transformer 2017 and vision transformers in 2020, many innovative segmentation models have emerged. In our image recognition system, segmentation is an important stage that helps to extract of their interest, and which is the further used for processing, like recognition and description and others. As you see this slide, there is some kind of mention about the transformer, vision transformer, and then others as a visual chat GPT, and then SAM. SAM is a gesture that showing in the this year, spring this year. And then there are just a few some other segmentation model, and then we just made it. That is our mobile SAM, and then July this year. This one is a faster and lesser computation requirement than SAM, we think. Okay, what is the segment anything? This SAM is by the Meta AI Research. It is the open source that generate high quality object masks from input prompt such as dots or boxes, and that generate masks for the all object in the image. This SAM has been trained on the data set of the 11 million images and 1.1 billion masks, and then it says that it has the strong shot performance on variety of segmentation tasks. Okay, as you see in this that figure, one that is masks generated by SAM from the single, that's a ambiguous point prompt. That is a turkey image. Okay, that that mask is a whole body, and then this just for this dots prompt is generate this body parts and then this head parts something. Others are similar. Okay, also it segment anything. This model can make that segment everything. Image. Okay, but this the SAM model has some limitations. It basically is so heavy weight model, even though it has the zero shot transfer performance. So that's this overall architecture of SAM, that it has the image encoder that module, and then imaging embedding, and then decoder for the prompt guide. And then for the prompt, it has the prompt decoder, right? As you see this, that image encoder is so big, big enough. These are 632 mega, then much for that parameters. But the decoder part is a little bit lightweight. Okay, this also that mobile, SAM has the many models. As you seen, that is based on the vision transformer huge, and then and vision transformer large, and vision transformer base. Okay, those has it has the different mask that achievement. Okay, what happened? Okay, that I believe that it is also July of this year that this fast SAM was appealed. It says it is also the lightweight CNN model, and then is that's based on the YOLO version 8 SAG model based. That it has consists of two parts. AIS is all instance segmentation, and then the other part here, below, that's the specific object of the interest that we say that's it PGS. But this is a CNN based architecture. even though it's it is significantly reducing the computational load, but it is not some kind of same cities. It's a totally different that's a foundation model, I think. Okay, this fast SAM is faster than 50 times than the SAM. Okay, that it also can segment that's everything, and also by pointing out that this some prompt by prompt. Then you can get some segment or part of the image, and then also you can use the box of as a segment. I mean prompt. Okay. I'm saying that is still that we need some more. I mean the right weight the SAM model. So replacing that heavyweight image encoder. I mentioned that it's with lightweight that's model, so that we observed that the current SAM model, as you've seen that previous slide, that is a front guide mask decoder in SAM is has less than 4 mega parameters. Is the considered right way. I mean. We saw, however, the default image encoder in the original SAM is based on the VIT that is huge, with more than 600 mega parameters. Okay, so it is shows that of the some kind of sorry, oh my goodness, is there. That we have the parameters with the different image encoders about the H and L and B, right? So that that two key the obtain mobile friendly SAM lies in the replacing the heavyweight image encoder with lightweight one. So that we like to try to make it that is that that encoder and decoder to be decoupled. So using that knowledge distillation method. Oh my goodness, something. I have some keyboard here. Okay, thank you. Okay. Yeah, before that having that our proposal, we tried some little bit different model for the that knowledge distillation. That firstly we try that is distillation that between the teacher SAM and student SAM using the that mask. That's all that we have some distillation process between the mask. Okay, that basically we use the Foucault and dice losses. For that that mask that can of this student SAM that is backward processing recursively to the prompt guided decoder and that VIT based then image encoder. Okay. Also, this one is still has some limitations. For the coupled optimization of decoder and encoder, it has the some kind of also challenging issue. It's difficult to optimize because that is some if the some image encoder changed, and then also that using that result that is a mask decoder is changed, so that it's recursively we doing that is optimized, that is so difficult to reach to the optimal than some goal. So that we second trial is we just frozen the prompt guided mask decoder, and then is from the teacher SAM. Okay, so we just copied and then doing the same process with previous that architecture. Okay. But it's still that if we user prompt is random, then which it is makes the mask decoder variable, and thus the increase the optimization difficulty. So that also only the encoder adapt to the random prompt, while the decoder cannot contribute to the such adaptation. Consequently, performance of the entire system may not be optimized. Okay. So that we propose to distill the small image encoder directly from the VIT huge in the original SAM without resorting to the combined decoder, which is termed decoupled distillation. As you see this in this slide, we have the here. We just copy the prompt guided mask this part, and then we just frozen this. And then for this encoder parts, we just distill. We got the knowledgeization for this that using that mean square error just. So not using this focal loss and dice loss. Okay, we do that is some kind of backward processing. Okay, to that enhance that encoding parts. Okay, so that it's a kind of we say there's a simple. We just use the simple MSA loss instead of using the combination of focal loss and dice loss for the making mask prediction. Okay. Okay. This formula, this formula is how to make the mask. That this basically using input image and prompt and the modern parameters can get mask image, and then we just as we used for the that the distillation is this mean square error. We approach the loss is I mean 2 to 0. We this tiny VIT can be approached to the VITH. Okay, this is basic way to we have the proposed. Okay, we have the some experimental that result that we have the set up the experimental environment for the actually meta trained SAM with the VITH image encoder takes the 68 hours on 289 800 GPUs, even replacing that VITH with the L and B reduce the recalled GPU to the 128. In case of our model, lightweight encoder, just need the 1% of the segment anything that 1B, 11 terabit data set for the 8 epoch on the single GPU, and can obtain the OSM in less than a day. Okay. Also, to make a distillation faster, we saved here image embedding beforehand so that we can only need to learn the forward process once. Okay, so that this is actually this one is some actual comparison of the computational requirement. Okay, so the coupled distillation performs better and requires that less than 1% computational resource than coupled distillation. Okay. Okay. Also, we measure the mean interaction of a union with that original SAM. This is as I showing this in the here. Okay, MIOU. This the coupled distillation is 0.75. Okay, so it's the more the better it means. Okay. Further parameter and inference speed that we have the last parameter, then also has the faster inference. Yes, sir. Do you see this? This is much less, just around 1%, right? For the speed, yes, sir. Yeah, it's much better. Evaluation study on the influence of the training computation is this, so that more patch and more iteration can further improve the performance, as you see, with the on single GPU. So that this is a kind of evaluation result from the human perception that mobile SAM performs similar with the original SAM, as you see, right? That's for the many images. Also, we compare with that between fast SAM I introduced, then mobile SAM. Okay, so some parameter size and speed is much better than that fast SAM. Okay. Yeah. Also, that fast SAM has the many stars, but less than hours. Okay. Yeah. Also, that this comparison with the original, SAM, that's result of our mobile SAM aligns surprisingly well with that of the original. Yeah, sir. Yeah. Okay, we have comparisons with the mobile SAM and original SAM and the fast SAM. Yeah, that mobile SAM and original SAM is a similar result for the segmentation, but fast SAM is a little bit that broad for these pillar parts. We can see that it has a non-smooth boundaries. Okay, this slide shows the application for the mobile SAM that we can use this for the social and photograph applications for the beautification, face segmentation, and face impending. And they also can use for the shopping applications. That, as you see this, so you can just see that some kind of one piece at how much what brand can help to make a decision for that. Okay, also we can apply this one for the vehicle identification, license plate identification. Okay, also we can apply this for the some identify the brand and vehicle condition and what model, something like that. Yeah, I like to conclude. This mobile SAM is on the GitHub. That as you see, this one is has the 3.5K stars. I hope that you can use it and then you can modify for everyone. Thank you.
Thank you, Jung-sun, for your great talk. So now we are going to have Q&A session. Please raise your hand if you have any questions. Actually, I have one question. So, your experimental result is so impressive. So, could you give some comments on some limitation of mobile SAM or SAM in general?
Yeah, good question.
Any failure case or something like that?
As I say, that is a MIOU. Yeah, actually, there's a 0.75. Yeah, not 1.0. It's a, but we believe that is enough for the mobile application. So, yeah, we can more do something optimizing that we can try to reach to 1.0. Yeah, that's I like to say that it's a limitation. Yeah, original mobile SAM itself. Okay, we think that we inherited that original SAM, but the fast SAM is not that one. Others that our model is a real student that SAM kind of. Well, that I believe that is okay. I believe that we can just make her that now that we got just dots application. I mean that prompt, and but we need to add more others, such as like multimodal, yeah, as our input, yeah, as our input prompt. Yeah, that's will be another challenging issue to have some then application of the SAM. Yeah.
Okay. Other questions? Okay. Thank you, Jung-sun, for
Thank you.
your talk again.
Thank
Okay.
you.